Swayam Prabha. Digital India. Educated India.
Hello everyone. Today we will discuss Iso-Parametric Formulation in finite element method. You see, the idea of finite element method is we have a domain and then that domain needs to be represented by a collection of elements. And these elements, we write the equations over each elements and then assemble and finally solve it. But the domain is represented by a set of elements. We already know what is triangular elements and we know how to write shape function for a triangles. You see, this idea representing a domain by a set of elements, one advantage is, of course, we cannot write equations, a single equation for the entire domain. We may not be having equation or even if we have an equation, we cannot solve the entire domain as a whole. So write the equation at the element level and then get a system of algebraic equation and solve it for the entire domain. Another advantage is if you have a complex geometry, these elements, through that element, this complex geometry can be represented. But then by now we have seen only two kinds of element. One is three-noded triangle, and which is also called constant strain triangle. And we have also seen a rectangular element. We have discussed in the last week how to write shape functions for quadrilateral elements in parametric domain, but we have not discussed what to do with that shape functions yet. So if we always use triangular elements and rectangular elements, then the basic advantage, the major advantage of finite element, the representing more complex domain, complicated domain is lost, because all domains cannot be represented properly through these straight-sided triangles and rectangular elements. And if we do not represent the domain properly, then we have already seen that domain approximation is one source of error in finite element, so that error will come in. We can reduce the error by increasing the number of elements, but still, if you have a curved boundary, that representation of that curved boundary cannot be proper with straight-sided triangle or quadrilateral. Now, in this context, isoparametric formulation is very useful. Now, before we start discussing what is isoparametric formulation and how it will make our life easier, I would like to take you to one of the slides in last week, just before we started discussing numerical integration technique over two-dimensional domain. You see, that time we had seen that when we discretize a domain with two-dimensional element, that's true for three-dimension as well, then we may not be having always, it's most of the time we cannot afford to have only rectangular elements or only so in this context we need to look for a new formulation, and that time we discussed, for the time being, let us understand how to write shape function for this domain, and then we will see in the next week what to do with this shape function, how this shape function is mapped with the domain, with an element in the physical domain. And this is the time today is the time when we will discuss this mapping. Okay. So before that, what we know is, we know how to write shape functions for parametric domain. We also know that how to integrate a function using using Gauss quadrature technique over this parametric domain. Okay, what are the integration points and weights? We know that. So idea here is we have a parent element which is always, in this case, let us have a discussion in the context of 2 dimension, then we will see in the 3 dimension also similar philosophy can be extended. This can be also applicable for 1 dimensional problem, but in 1 dimensional problem the major advantage, we don't have those difficulties what we have in 2 and 3 dimensional problem. That's why this is very important, formulation is very important in higher dimension. Now, idea here is we have a parent element, and then we need to define a map between a parent element and a physical element. Okay, and this map is, and how to construct this map and how this map is to be taken in the formulation is the topic of today's discussion. Okay, now let's understand what is the concept of isoparametric formulation. Suppose we have an element. Just for the demonstration, I am showing you 8-noded quadrilateral element, but the idea is same for any other elements as well. So this element is in its physical, with respect to its physical coordinate system, xy coordinate system. Okay, this is the physical domain. Now suppose any function is defined over this element like this, and we know this function can be represented through the shape function, right? So this function is, if any function u within this element can be represented by this, and phi I is the shape function and n is the number of nodes in the element. We know this, right? But remember, we have not yet discussed, so far we know how to construct this shape function, what to derive these shape functions for an element in its parametric domain, okay, with respect to the natural coordinates, right? We really do not know as of now that what this phi will be in this domain, because essentially this function is to be approximated on this domain, right? Now, so we will see that that's the reason I have not given in the bracket whether it is a function of its physical coordinate or the function of its natural coordinate. We will see that. Now let's take a domain which is defined between -1, 1 to 1, 1 in xi eta coordinate, and xi eta are the natural coordinates, right? We have seen this these coordinates. We had a discussion on this kind of parametric domain in the last week. Now we want to define a map between this domain and this domain. So between this domain is called the physical element, and this is called the parent element. So we need to have a map between the parent element and the physical element. Okay. Now, so this, and another information is, we know that on the physical element, any function u is defined, is approximated over the element like this. U, I are the nodal values and phi are the shape functions for different nodes. Now, let's understand the idea of isoparametric element from its name itself. Iso means something equal or similar, right? And the parametric means expressing something in terms of some parameter. Okay. So the isoparametric means then expressing in terms of similar parameters. But the question is, what to express? Expressing what? Now, expressing field variables and geometry. Field variables, we already know that field variables over an element is represented like this. U is the field variable. It could be temperature, it could be displacement, or it could be any other degrees of freedom depending on the context we are using this element, but we know how to approximate field variables. Now the idea of isoparametric element is the kind of approximation you are using for field variable, same approximation can be used for the geometry. Now, what is the meaning of expressing geometry in terms of similar parameter? It means, see, in natural coordinate system, our domain is a square domain, right? Whose length is -1, whose coordinates varies from z direction -1 to 1 and eta direction -1 to 1. And we have written our shape function and the quadrature rule, everything with respect to this parent element. Now, this is the geometry of the parent element. Now, the geometry of any element in its physical domain could be anything, right? Now, this geometry needs to be mapped. Now, the idea is the shape functions that we are using to approximate the field variable, use the same shape function to approximate the geometry. We will see how it is to be done. So, it means that geometry means what? Geometry means we need to, at any point in the parent domain and any point in the physical domain, say point x and y, how this point is mapped. So, if we know any point in z-eta coordinate system, and what would be the corresponding point in the xy coordinate system, that will give you the geometry. So, geometry is mapped like this. The coordinate is mapped like this. So, it means that we know z-eta and then phi I z-eta are the shape functions on this natural coordinate, on z-eta coordinates. Okay, we know how to do that. Xi's are the nodal coordinates of this domain in the physical space, physical coordinate system. Okay, so this is also known. So, for any value xi and eta is represented to any coordinate, any value x and y, like this. Okay, and then field variables over this element is also represented by the same shape function. Okay, so it means that just now, as I said, if we take any value xi and eta in its parent element is represented or is mapped to xy, which is the image of this in its physical domain, by this mapping. Okay, so this is the idea of isoparametric, the concept of isoparametric element. Now, what we have to do within this concept, we have to rewrite these equations. We have already written these equations in terms of xy coordinate system. Now, with this new with this concept now needs to be integrated with the equations that we have already derived. Okay, now, so some examples before we do that derivation. Let us see some examples. So these are some quadrilaterals in parent element and the corresponding quadrilateral in physical element. So you look at the parent element. In the parent element is always between -1 to 1 and then -1 to 1 in xi and eta directions. Okay, and then but in parent element the elements in the parent domain, the elements are all square. Okay, but when it is mapped through this gives you this kind of element. Okay, this is where sides is linear. In this case, the sides is quadratic, means this is quadratic sides, and in this case sides are cubic, right? And in this case sides is linear. So similarly, we can have for other kinds of element as well. For instance, if we take a triangular element, so this is parent element. We have written just in last week what are the quadrature, how to perform integration, what are the corresponding integration points and weights in a triangular element. But we have not talked anything about a natural coordinate system or area coordinate system in triangular element. We will do that in week 10. So this is how, when a triangular element is mapped between in its parent element is mapped with the physical element. Similarly, same thing can be done in case of three-dimensional as well. Here these elements are, your natural coordinates will be xi, eta and zeta, and corresponding physical coordinate will be x, y and z. Okay, so now we know what? We know how to construct shape function over parent element, and then once we know the shape function, then through this shape function, any point in the parent element, say xi, eta, can be mapped with the corresponding point in the physical element. Now the question is, see, it is very easy to say that we need to map it. Any point here xi, eta is mapped with this, but the question comes whether this map is unique or not. By unique means suppose every point, if we take in the parent element, whether the image of that point, when the point is mapped in its physical domain, whether that image lies within the domain or not. For instance, if we have a two domain, one domain is this, another domain is this, and we have a this is your parent element, and this is physical element. Now any point if we take, now this point when it is mapped through a transformation, through the transformation we have already seen, then these points should have an image within this element. Okay, so this feature is called onto feature, means onto. When any point if we take, that point should have an image within the element. But then it is not sufficient. Now, consider a situation like this. We have a domain here, another domain here. We take a point, and then this point, when we get the transformation, through the transformation, when we take the image of this point in the physical element, if we can have something like this, means one point through this transformation if we do, then we can have 2 points. Okay, or say here we have 1 point, and then 2 points can be mapped to just 1 point. For instance, just to give you an example, if we write fx is equal to x square, then x is equal to plus 1 is equal to plus 1, it gives you, x is equal to plus 1 gives you 1, x is equal to minus 1, also it gives you 1. So plus 1 and minus 1, two different points, but when it is mapped through this transformation, then we have x square, but the image of this will give you the same. That should not happen, right? So then in addition to that, this is called another thing should have is 1 to 1. Means if we take 1 point in the parent element, and then we should have only 1 point in the physical element. Okay, we cannot have multiple points, multiple image of the same point in the physical element. So these together, a map which is onto and 1 to 1 is called bijective map, right? Bijective map. This is very important. Otherwise, this transformation will not be unique. Okay, because we will see that we need to invert this transformation as well. So just to give you some example, if we have a parent element is like this and the physical element, for some reason, suppose if we have something like this, then this is not acceptable. Okay, you will not get a unique map, whereas this is absolutely fine. So this needs to be taken into account. Okay, now, so next what we do is, so we understand the concept now. What we will do is, now let us integrate that concept in the equation, and then let's see what the final equation looks like. So if you recall, this was our the weak form, and let us write all these. Yeah, this was our weak formulation. It was the element level equation, and this is how this coefficient matrix written. B is equal to this, which involves derivative of this f function. N is the number of nodes. Okay. Now let us see. Now these entire equations, all these equations written with respect to xy coordinate system. Okay, now now we have all these f functions, integration, everything we are doing on parametric domain. So but we know the map between the parametric domain and the physical domain. Now we need to put this map, integrate this map in this equation. Okay, let's do that. So what we know is this, right? We know x is equal to we know x is now another important thing you see that just a minute. Okay, see another interesting thing is if you see the equation, that equation involves derivatives, right? Now we know how to transfer xi eta when we have xi eta, how to get corresponding xy. We also need to know how to transfer this derivatives, how to map the derivatives with respect to different coordinate system. So what we know is xi, x is equal to we know summation of phi I into xi, right? Phi I written in term in xi eta coordinate and then xi, where I is equal to 1 to n. It is the and similarly y is equal to this. Y is equal to summation of I is equal to 1 to n, and then this is phi I. Phi I is written again in xi and eta coordinate, and this is yi. Okay, this we know. Now we can write like this: the derivative del xi can be written like this: del x del xi, then del x plus del xi into del y, and similarly del eta can be written as del x del eta, then del x plus del eta into del y, okay, by applying the chain rule. Now from this combining these two, this will give us del xi and del eta. That will be something which is del x del xi and then del y del xi, del x del eta and then del y del eta, and then this will be del xi del eta. Similar thing we have already seen in case of when we discussed numerical integration technique. Okay, now this is the Jacobian. This is called Jacobian, right? Now x is already this and y is already this. If we substitute x and y here, then expression for Jacobian will be something like this. Our expression will be summation over I, then del phi I del xi xi, and then summation over I del phi I del xi yi, and similarly summation over I del phi I del eta, then xi, and summation over I del phi I del eta yi. This is our Jacobian. We have seen this Jacobian before, where this phi I is expressed in terms of xi and eta. It means this phi I is constructed over the parametric element. Okay, so now we know this Jacobian. Let us quickly see what was the expression for B. expression of B was integration of coefficient matrix was integration of B transpose CB, where in this case C is constant, and B involves derivative of the shape function with respect to the coordinates. Okay. Now, if we take, say, quadrilateral element, 4 noded element, then the n will be 4. If we take triangular element, the n will be 3, and so on. It depends on the number of elements. Now, let us write the expression for B then. So, expression for B will be, so we know that B is equal to del phi 1 del x, and this phi 1 is x y, is expressed in as a function of x and y. Then del phi 2 del x, del phi 3 del x. This is for your this is for triangular element. If you have a 4 noded quadrilateral element, then del phi 4 del x, and so on. Then del phi 1 del y. This is also function of x and y. Others are also function of x and y. I am not writing it explicitly. Del y, and then del phi 3 del y, del phi 4 del y. Okay. So, now we have already seen that derivatives are represented like this. Derivative are there is a mistake here. This should be del x del yeah, just a minute. This should be x, and then this should be y. Okay, x and y. Okay, so if we know, if from this what we can write from this, that del x del x del, and then del y is equal to Jacobian inverse of Jacobian del xi del eta. Okay. So, now here the derivative is represented, derivative is transformed like this. Okay. Now, if we substitute that in this expression, what we will get is B. Now, here B is written in terms of x and y. So, B as a function of xi and eta will be represented like this. So, Jacobian inverse, and then the same thing we can write del phi 1 del xi del phi 2 del xi del phi 3 del xi del phi 4 del xi, and similarly del phi 1 del eta del phi 2 del eta del phi 3 del eta del phi 4 and del eta. But now this phi is expressed as a function of xi and eta, expressed as a function of xi and eta. Okay. So, this was written as a function of x and y, and this entire B is now written as a function of xi and eta. Okay. So, we know this is our expression. So, what was the coefficient matrix? Coefficient matrix was, if you recall, coefficient matrix was integration over the element domain, and then it was B transpose, then C and B, and then this is dx dy. Okay, integration over the element, entire element. Now, this entire, now B we know in this, when we write in this equation, the B is a function of x and y. Now, the entire integration, entire thing can be integration, can be rewritten, can be expressed with respect to the parametric domain. So, dx dy can be represented like the determinant of Jacobian d xi d eta. So, then entire thing we can write this integration, then B transpose as a function of xi eta, B as a function of xi eta, then C, B as a function of xi eta, and d xi d eta, and then we have Jacobian as well. determinant of Jacobian d xi and d eta. Okay. So, this will give us our coefficient matrix. Now, further we can express this if we have to do it numerical integration. This can be expressed as that integration over integration I is equal to 1 to say n gp. Gp is the integration Gauss point rule, and j is equal to 1 to n gp. We have already seen this, and then we need to wi at the wi and wj are the weights for at the integration point. Then the Jacobian determinant of Jacobian needs to be evaluated at xi I and eta I, and then entire thing B transpose need to be evaluated at xi I and eta I and C, and then again B needs to be evaluated at xi I and eta I, and this will give us K. Right. So, you see, so now once we have transferred this, means all these shape functions that we have written in term with respect to parametric domain, then integration rule we know with respect to parametric domain can be obtained. Okay. Now, so we just understand the theory now. In the next class, we will take an example, the same example of heat conduction we had taken in the last class. We will do that in the next class as well, but in the last class we used triangular element. Next class we will take a quadrilateral element where we use this concept isoparametric formulation and then see the solution. Okay. So, now next is another important thing is, you see, when we say isoparametric element, so in isoparametric formulation we have two kind of approximation. One approximation is approximation of the field variable and approximation of the geometry. Now, approximation of the field variable means over an element, if you approximate say temperature or displacement or anything, how to do that. And approximate of geometry means how to map between geometry of parametric domain and the geometry of the actual element. And in isoparametric formulation, same kind of approximation we use in both the cases. And then the question comes, is it really necessary always to have same kind of approximation? For instance, is it possible that we need higher order approximation for a given problem? We need higher order approximation of field variable, but the geometry is such that we may not need higher order mapping, higher order approximation of the mapping. Maybe linear map may work. Or sometimes it may so happen that our geometry is very irregular, so that we may need higher order mapping, means higher order approximation for the geometry mapping. But then field variables defined over this irregular geometry may not require that higher order approximation. Suppose our displacement field is linear or the stress field is linear. Okay. So what approximation we need for the field variable and the approximation we need for the geometry may not be same always. For isoparametric formulation, we take them same, but for some cases we may have different approximations as well. For instance, I have three kinds of parametric formulation. The first one is the isoparametric formulation. Now the dots, the red dots, these are the nodes for approximating geometry, and the yellow triangles are the nodes for approximating the field variables. You see, in the first case, isoparametric case, three nodes here means your approximation is quadratic, right? This approximation is quadratic. So same level of approximation is used for field variable and the geometry. Now look at this element, the second one. The nodes for approximating geometries is this. So for geometry, we can higher order approximation is used for the geometry. More number of nodes are used for the geometry, but for the field variable, less number of nodes is used, means the order of approximation is less. It is the case where you have irregular geometry, but over the geometry your the stress field or the displacement field, they may not require higher order approximation. Okay, this kind of element is called super-parametric element. Now another case is where your geometry is relatively simpler, so you may not need more number of nodes or the higher order approximation for the geometry, but the field variables defined over the element may need higher approximation, and in that case you need more number of nodes for approximating the field variables and the less number of nodes for the approximating the geometry. This is called sub-parametric element. Okay. Now, so as I said, that example we will do in the next class, but before we stop today, one important part is, you see, we can do anything and everything, provided this should not, whatever mapping we do, whatever addition we do, concept we integrate in the equation, but that should not violate the basic requirement of our weak form and the subsequent finite element method. For instance, completeness is one important thing we have seen. We have seen that global continuity, the minimum requirement is we should have global C0 continuity. Within an element, we should have at least linear, our approximation should be such that a linear field can be approximated. Our shape function should be such, our linear field can be approximated. That is the minimum requirement. So, whatever mapping we do, it is very important to check that this is not violated. Now, what next we will do is just to see whether it is violated or not. And first, let us see that. Okay. So, first we will see whether because of this isoparametric formulation, linear field is violated or not. Okay. Now, so linear field violated means, linear field means what? If we have a function f, this is the function of x and y, say x and y, and this can be represented, say alpha 1, or we have used probably C1, C2, C3. So, let us use that. So, we have used C0 and then plus C1x plus then C2y. This is the linear field, and if you recall, in triangular element we started with this approximation only. Okay. So, this is the linear field. Now, isoparametric formulation will give us this: x is equal to summation over I is equal to number of element, and then phi I and xi, and similarly y will be summation over I, this will be phi I into yi. This isoparametric formulation will give us. Okay. No, okay, this is the approximation of the geometry. Approximation of the geometry. Now, if we approximate the field variable like this, suppose f of xy is equal to summation of I, then if summation of I and then phi I and then fi. Fi is the function value evaluated at the ith point. This is for the field variable. Okay. Field variables. Now, isoparametric formulation is this: geometry is approximated through phi and the field variable is approximated also to phi. So, what we want to check is this additional requirement, the geometry is also mapped through this phi, should not violate the completeness requirement, the minimum requirement, the linear field is approximated accurately. Okay. Now, so if we do that, let us write phi x. What is phi I? Phi I will be phi at xi and yi. Okay. And this will be equal to C0 plus C1 xi plus C2 yi. Okay. So, fxy, that is equal to summation over phi I and then fi can be obtained from this, which is C0 plus C1 xi plus C2 yi. That will give us summation over phi I into C0 plus summation over phi I C1 xi plus summation over phi I, then C2 yi, all are summation over I. So this will give us C0 summation of phi I plus C1 summation of phi I xi plus C2 summation of phi I yi. So these up to this, it is only the approximation of field variable based on this approximation. Now what we'll do is we'll integrate, we'll put this information in this equation. When we put this information in this equation, then only our formulation becomes isoparametric, right? Now when you put this information here, so phi I is the partition of unity, it satisfies partition of unity, so means its summation of phi over all I should give you 1. So this is C0, this is an important property, we had verified it, and then we had also said what happens when this partition of unity property is not satisfied. So this plus, now phi I xi gives x, so C1x plus phi I y gives y, this is C2y. So this is phi xy, which is same as this approximation. You may be thinking that it is very obvious, but let us try, or you yourself try. This is for linear case. You can try what happens when you have your approximation quadratic, means in this case you have your quadratic term as well, and then check what happens. Okay, now so that I leave it to you. So then what we have seen is that this isoparametric formulation does not violate the completeness requirement. Okay. Now with this we will stop here today. Next class we will take the heat conduction problem and then discretize with quadrilateral elements and use this formulation to get the solution. Okay. Thank you. See you in the next class.